All right, ladies and gentlemen, today we'll continue our talk on vectors as we are finishing off Unit 0. Last time we talked, we showed that you can add vectors in any order, and then when you were doing the lab vector, we saw that we can add those as well as it asked you to, and some of you will have to make sure that you stay on top of that. When we have vectors, and this will be a common thing, you will have objects being pulled in one direction and then being pulled in another direction, and a lot of times that will make that parallelogram that we have. And then but parallelograms aren't easy to solve for. But we know certain things about parallelograms that should allow us to make the triangle. Triangles make our lives easier to solve. Triangles are there. As we can see, if you add it tail to tip, that's what it would work. But sometimes that's not how the problem gives you, okay? And it might say that the velocity or the force, okay, this becomes a thing, right? Even though we haven't talked about it or looked at how to solve it, they get brought up because that's how a lot of vectors are used, is with the force. A force is pulled due east. That would be like our V1. Okay. Then there is a force that is, obviously V2 is not at a straight north angle. It might say that it's 10% or 10 degrees east of north. What that tells us then, that if it is a 10 degrees east of north, that it's from the north going east, and that's where the 10 degrees is. So if the black arrow that I drew up there is 10 degrees, what would the blue angle be left? Well, if we look at our coordinate system, that yellow would give us a 90-degree angle, right? If the black arrow is our 10 degrees east of north, what would be the blue angle be? 90 minus 10 is 80. So it would be an 80 degrees north of east. See how we have two different answers and they're giving us the same thing? Okay, so that's where sometimes that's going to happen in your homework and or how things are reported. And we have to just be careful reading the problem. Okay? When many of us went through stoichiometry, the devil was in the details. In physics, the devil's going to be in the details of how they say what's going on. And that can be, are they talking about east of north or the other? Now, sometimes at some point we'll get into a rhythm where we will always say from the horizontal or above the horizontal, meaning the horizon, the straight line. Okay? But in this case, I would see it easily saying that it's 10 degrees east of north. The blue line would be that 80 degrees north of east, as we can see it moving up to closer to the north. Now, how does this all come together? If we are talking about it as more of a velocity, the velocity car went v1 this fast due east, then the road turned and continued at the same speed, but was at 80 degrees north of east. That's where our V2 comes in. And that makes the tail to tip easy because it's in sequential order. What doesn't happen is, say if it was, we were talking about forces. Somebody on one side of the dock pulls a boat with a force of V1. Somebody on another dock pulls a boat with a force of V2. And that usually, that could happen where you have somebody pulling that way, somebody pulling that way, and the resultant, what we see happening, is that. It's the sum of the two forces. Somebody pulling on one thing at an angle, somebody pulling at another thing at an angle, and the thing still moves forward. How do we solve for those things? How do we solve for the resultant? We use what we know about vectors and triangles and take it and complete that triangle, and now we have a triangle. Because this can be easily just moved from one side to the other. We're not changing anything, we're just changing where it's at, right? And so therefore now we have a triangle, and you're like, sweet, I got a triangle. Not only that, chances are you're gonna know maybe that angle. If you don't, that's okay, because you might know this angle, which means then you would also know that, potentially that angle, or you might know that angle. Okay? We talked about before in calculus, you can solve for two unknowns. In algebra, you don't get to do that because it's really hard. You get one unknown. So you have to try and figure out, okay, I can use this to find this. Okay, that gives me a known, and I still have two unknowns, but if I find this and I find this, I'll be able to find this. So sometimes it might take you multiple steps to find everything so that you get that one unknown to solve for it. What doesn't work is the last one, where you're trying to have that work. Where you're having tips to tips. Usually doesn't work that way. It's not how physics works. Because if somebody was pulling on something in one direction, if someone pulling on something in another direction, the object doesn't move in that incorrect manner. It would move in the parallelogram. So the order that we have does sometimes mean something. And we should also get into the understanding that vectors can be negative. Velocity can be negative. Acceleration can be negative. A force can also be negative. Time, however, cannot be negative. So when we're solving for some of our equations as we move forward, we will go, oh, hey, somehow I got a negative time. That should mean something went wrong. Okay? Time is a scalar quantity, and therefore can't go negative. Vector quantities, because they have both direction and magnitude, oh yeah, they can be positive and negative. Because as Vector says, he commits crime in both direction and magnitude. Well, that means there's got to be something that's trying to oppose that vector as well. So that's something that we'll look at and get easy. So negatives can mean speeding up, slowing down, or decelerating. Okay, but also they can mean that you're dealing with, say, if we look at our quadrant here, I remember my math class saying that that quadrant is plus plus, right? X, Y, and then we go X, Y, negative plus, negative negative, plus negative, if I did that right, memory serves me right. Okay, that because in that X, Y quadrants, you can have things moving in both negative parts, and this just means it maybe starts in, we always called it the third quadrant. As we number our quadrants. Adding of the vectors when they are at different scales, drawing out what we see, very important. Okay. Multiplying our scalars, sometimes this will come into a factor when we're drawing things out. Say you're using a vector quantity that is really small and really hard to draw, so therefore you need to adjust everything by a scalar. Okay? In the lab that you did, you had to use a scalar. The force that you were finding using the rubber bands and the water could have been done. It would have been small, that amount of force. So you use a scalar to up that amount. And so we are able to draw them out in a scale that would allow us to, in some cases, as you kind of find in, I believe, part B of that lab, you're able to measure the resultant within reason of your answer that is calculated. So sometimes you have to use a scalar. Sometimes you don't. Sometimes they're really nice. They're like 5 newtons or a velocity of 5 meters per second. So you just make 5 be 5 centimeters or 5 be 5 millimeters, depending on how big you draw. 5 millimeters, really small. So it might be better to go 5 centimeters. Bigger, easier to see. Right? Get too big, then your paper gets too size becomes an issue. When you do have scalars, the sign needs to stay the same. So if it's already a negative, you would want to make sure that it also is a negative. So that becomes a thing. So we want to make sure that we have the signs are right, the angles are right. Just because you scale something up doesn't mean the angle changes though either. Actually, it doesn't change at all. If you double your scale, that doesn't mean you double your angle. Okay? You don't go like, oh, it's at 22 degrees, doesn't mean that it jumps to 44. The scale of the vector is still there, but the angle at which they are doesn't change. Okay, so we want to make sure that that becomes a thing. Most of the time, we're going to look for the ideal situation that we're able to get things into a nice 90-degree angle. Why do we want things at a nice 90-degree angle? That's because we can then use our sine, cosine, tangent more effectively. Then our whole sine, so, ka, toa use can be used. Sometimes we're not given the other parts. And therefore we have to figure out, how do I get to that part? Maybe we're said that an object is launched at a velocity at a certain angle above the horizontal. And we're going to go, okay, well, how does that work? Because projectiles, their path is not one of straight. It's a curved path. So how do you solve for things with that? Again, using algebra. At this moment in time, normally we would, sometimes you're like, well, remember when we used to be able to use water fountains? Water will come out like that. Follow a curved path. Well, it's the same thing if I threw an object at you. It will start falling at some point. If I threw an object, say, from the front of the room at a student, it would drop. And it's going to drop at a certain rate, which means that it has a curved path. We only see the back end of the curve that way. This just didn't happen. You watch football either tonight, because I'm pretty sure the teams will be punting a lot, or on Sunday, you will see the punter kicking the ball, and it comes down. Okay? And it's sometimes they say, oh, it's a line drive one, which just means less angle, less opportunity for the guys to get down the field. So those are interesting, but we can't solve for finding the parts with a curve using algebra, unless we use some triangle work. If we zoom in to that area, we can envision that that arrow is the same. It's the object that's launched, just say, at a 30-degree angle above the horizontal. We now have information, and we're like, well, it could be, and those of you that have taken calculus, is how do you find the area of a curve? How do you find the area underneath a curve? Those who have taken. You don't want to know?
No, you just shouldn't try.
You shouldn't try, okay. But it's possible, right? Yeah. Okay. I remember when I was taking calculus, they talked about, okay, you just basically are finding really small rectangles, right? And then taking into account that this little area above the rectangle gets taken into account still, right? Well, those are just like little triangles. You zoom in enough and you get small triangles, or get little rectangles, you will get little triangles above. It just curve keeps changing a little bit, so the angle kind of changes, but that's just what it is. And with those triangles, we can make them right triangles, where the X would be like the top of the rectangle, right? This is still the projectile's path. We then have the ability to say, okay, that black arrow would be kind of what's happening of why it sees that, because it's going up. We can move it over here to complete our triangle. And now we have a solvable solution. Not only that, we got a right triangle on our hands.
So you can integrate.
Or one could integrate, but why? Some of you are like, I don't want to do that. So don't. If you know the red line, you can find, with an angle, you can find the green and the black line pretty easily. So katoa. Right? So utilizing those parts. Sine, and it's the angle that I have written there, that's the theta. A lot of us will just go this way. Opposite over hypotenuse. Adjacent over hypotenuse. Or opposite over adjacent. And the last equation, b squared is equal to vector squared is what they get. Looks a lot like c squared is equal to a squared plus b squared. Right? And remember, that's where we get our ka toa. Sine opposite over hypotenuse, cosine opposite. That's adjacent over that. Why am I? There it's adjacent. Over the hypotenuse. And then tangent is opposite over adjacent. When we have equations that are boxed in some manner, feel free to put them on your equation sheet, as it might be beneficial so that you can reference it if you need it. Some of you might go, I got this, but I think everybody at some point in time in taking a test will find themselves all of a sudden blanking on some of the very simple things. And so, at minimum, I would write down what's inside the box. You may even write that in the equation box if you need to. As long as you have what's there. And yes, now some people go, I thought we weren't supposed to write words. Sine, cosine, and tangent are really the only ones that you get to write. Another way of doing it is when we don't have 90 degrees or a nice 90-degree point. We have the law of sine. And the law of cosine. I have even seen and never told students that they had to remove if they had the triangle that is written in the lower right hand corner of the slide that has the A, the B, and the R, and at least the theta recognized. So those are some other items that would be on your equation sheet. Most people don't have the law of sine or the law of cosine memorized. That's what an equation sheet is for. I got equation sheets when I was in college. Chances are you would as well. I don't see why at the high school level we need to have you memorize every single equation potentially used. Those of you that go on to bigger and better things and some higher end physics, they might not let you have an equation sheet and you just derive, and yes, I use that term correctly, all of your equations. Or they'll give you one and say, all right, derive all equations from this.
That's what I would do in Calc 2, so it's not fun.
So it is a thing. I always prefer, let's not stress out more than we need. Okay? So when we have motion, and we're usually a lot of times we're dealing with it on the surface of the earth, that's one of the things that we can infer. So often it's convenient to have that x and y axes, as we've been talking about a number of times. The y axis always usually pointing north, and that would be our positive y axis when we're dealing with that. So that's going to be our positive y axis. Therefore, this would be our positive x axis. This would give us that positive that we had talked about in the previous slide as well. Now, one of the other things that we will tend to do on these types of problems as well is we will see that we will have some other things going on. And so the emotion involves moving through the air. A lot of times what we're going to see is we're going to have objects kind of falling off of a cliff. And so sometimes you will see a cliff just drawn that way, and then the object being projected and then falling off the cliff. Maybe it is going to then land on an object below, whatever it may be, or it will splat and hit the ground, whatever it may be. That's what it is, and that's how we have. And sometimes we even have objects going up a hill. So you can also see objects being fired in the direction up, and therefore we can then see what's happening as it flies through the air. And that's where having these x and y axes, understanding what's going on, is so important. That's the drawing out of the vectors and the physics problems that we do are so important. Drawing out what's going on is going to be such an important part of it. So our first real good problem begins us with the boat problem. And as I said previously, it's good to draw some things out. So we're riding a boat whose speed relative to the water is 6.1 meters per second. The boat points at an angle of 25 degrees upstream on a river flowing at 1.4 meters per second. First thing that we need to solve for is this velocity speed relative to the ground. And if the speed of the boat remains the same, meaning 6.1 meters per second, but the direction in which the boat points changes. What angle is required for the boat to move directly across the river? So I'm going to resize the question here so that I have plenty of room to do the problem. Because again, drawing some things out is going to be important for us in this problem. And so we will want to kind of show our shore. Okay, we'll have our shore here. Just draw it in here terribly. And so that will be there. I have the water, and I will use just some arrows as the water is flowing here as well. And all of those arrows should be about the same if I had drawn them out perfectly, and they would be moving at 1.4 meters per second. So I'll just write 1.4, and one of them maybe I'll write our meters per second. Now our boat we'll make that a different color here. Make something a little bit more sporadic. Okay, our boat is going upstream, so that means it's going against the current a little bit, but it's 25 degrees upstream on a flowing river, meaning it has a angle pointing. And see, I'll just draw a little boat here. Not the best boat, but it has that, and it has an angle of 25 degrees. And when I draw that, it would be 25 degrees right there. Now the boat has a vector quantity of 6.1 meters per second. Now, there's a lot going on here, so we're going to have to redraw some of this stuff to kind of get rid of some of the extra things that we have going on here. So I think it might be better to draw out one of my 1.4s and then connect that with my boat. And even though I'm not using the correct colors of that, and the reason why I'm doing that is because I think it's going to be very valuable for us to see the differences, especially at the beginning, between those items that we have. And so I think that's going to be more important than drawing the vectors in the correct color. And so my 6.1 meters per second. Now I'm going to draw my X and Y axes here, and I think I'm going to try and get some dotted lines kind of added in there. My angle here, remember, when I had it out, there was 25 degrees. I know, mathematically speaking, that then this angle right here is also 25 degrees. I am going to be looking for it relative to the ground, the speed relative to the ground, which would be the red. So I'm looking for the red side. Because the 25 degrees now is cut up, it makes life a little bit difficult. However, because this is also, use the wrong color, because this is also 25 degrees. I know if I completed the right triangle part of it, that I should have then 90 minus 25 would give me this angle inside here, and we'll draw it with a couple arrows, would be 65. Now, I should have enough information, actually, to utilize the law of cosine to find out what my red is. So I will have the law of cosine of r squared. I'm going to try to make sure the colors are in the same, or the correct thing. And we'll say is equal to, and it really does not matter if I use which one I use for this, and I can say that it's 6.1 squared plus 1.4 squared minus, and I'll try and go general on this one, the 2, and that would be multiplied 6.1, and then the 1.4, and then times the cosine of theta, which in this case is going to be 65. Now I'm going to do some of this step by step with this as well. So I will do some of the calculations off screen on my handy dandy calculator. And my handy dandy calculator should be an ACT approved calculator, as should yours as well. So for the first part here, I am going to use, I'll use the blue for this at least part, and to give me 39.17, to give me that. Then I will do this second calculation, again, off screen, but you might be able to hear the little punching of the buttons as I'm calculating things up. And that all together gives me, because I remember I got to subtract it, 7.22. Then I do my subtraction of 39.17 minus 7.22. Usually better to keep full calculator readouts to get a rounded value. And we'll keep that r squared there. Maybe we'll even change the color like it's that I had before here. R squared, because that's the color I'm looking for, is equal to 31.95. But I need to square root both sides so that I get rid of the square there. By taking the square root, I am going to find that red part is 5.65 meters per second. Now, one could further say that you need the X and Y axes parts for that as well. I don't think it's necessary at this time to do that. I think just finding out your X's and Y's will be good enough practice, or finding out just the 5.65 as a good practice. Now the last part, we're asked to find it a little bit differently. Is now kind of utilizing that same drawing, that river's still moving, but now we want this boat to move across at a true 90-degree angle. We want it to go all the way straight across because it will get moved. So what angle do we point our boat to get it that way? And many of you who've been on a boat or driven boats have an inherent knowledge of what way to do that. So we're going to do it a little bit differently, and I'll use some math for us here because we have some of our numbers already. We know we're going to have part of our triangle is going to be the 1.4 meters per second. We also know that the other part is going to be our 6.1. Now, cover that. Our red, we want to find out what that is, and so opposite over adjacent, or over that. Opposite over adjacent, and that will give us, oh, I actually drew this out wrong. Nobody ever says anything to me about that. Right, use the right color, but I must have been looking at it wrong. I used the right color. I had the right color drawn, which means that's the right one there. That's where you have. And we're looking for that angle what angle will get them straight across. And so we can use the sine of theta is equal to opposite over hypotenuse, so 1.4 divided by 6.1 to give me 1.4 divided, not times, divided by 6.1, and then do an inverse sine of my answer to give me an angle, and a lot of times written as just that, of 13.3 degrees. A lot of work to solve that, but we got two parts to answer here as we have our one big example with that. You'll find many more examples going through labs and the practice problems as well. All right, there ends Unit 0 and the talking about the kind of the things that we need to use and information that we're going to need moving forward in Unit 1, 2, 3, 3.5, and so on and so forth. So this is just kind of that building unit, and we will continue to go through these things in class, through the labs, and through practice problems.